this. So you are allowed one cheat sheet, front and back. Okay? Like the other one, it's out of 105 points. Yes.
Is the final open book? Open my notes?
Yeah, the final is traditionally open note and open book because that's what the other professors want. I find that to be a hindrance. Having open book won't help you unless you actually know where to find it. So it's better to just have some notes and bring it with you, or just better to prepare a cheat sheet. So the exam will look pretty long, but that's just because I give you a lot of space to work, right? Because there's less coding on this one and plenty of drawing. Right, there's like 3 coding questions. You'll maybe have 35 points of coding points on this exam because there's just so much that's not coding, right? Again, if your answer is really, really good, you can earn extra credit beyond there, but otherwise it's pretty good. So the first thing that I like to ask is this kind of question. So basically, for this data structure, tell me what kind of data structure you should use for this scenario to model this scenario, right? So not just how data structures work, but what should you use? And on the exam, I might I'll probably have you ask you to give me a 1-sentence justification, no more than 1 sentence, because otherwise you'll use way too much of your valuable time on 3-point questions. So so you need to model which patient should be seen next at a hospital. Patients should be seen in as close to order of arrival, but patients in a more severe situation should be seen first. So that data structure is what? Priority queue. I'd also accept heap, right? I would also accept basically the thing you use to build a priority queue is just a heap, right? Is that because priority queues basically are good for people needing to cut in line. So a router needs to hold packets in a buffer and deal with them in the order they appear. That's a regular queue. It's just a regular queue, okay? Because first in, first out operation. You need to model some kind of hierarchy.
Tree.
That's a tree, right? Generalized, just plain old tree. Notice that I didn't put binary tree up there. I just said tree, right? You need a data structure to hold your previous decisions in case you need to backtrack. Yeah, that's a stack, not recursion. Some students put down recursion. That just means they don't understand stacks. You use a stack. A recursion is not a data structure. The stack is, right? So you need a data structure to hold your previous decision in case you need to backtrack. Now, for you guys, right? I think this semester you might take the same exam as the other class, but traditionally I was writing a different exam for you guys, and we might because you don't take it in the common session. So and that amounted to not too much of a difference, maybe a 10-point average swing actually, but that's average. We're talking, I say that's not big of a difference, but that changes the average on the final from a 53 to a 63. So and that can be accounted not necessarily for me being easier, but simply because you have more familiar questions to deal with. So but I'm in charge of writing the final this year, so not really going to matter at all. But anyway, so yes.
I'm sorry. You said the difference is going to be in the final.
What?
The final is different than.
It has been because there's a common final right before it. So typically, what happens? Yes.
Wait, I forgot where the test is taken.
In your lab. In the lab.
All right.
Okay. Yeah.
You were talking about our final is different from the rest of the other people?
It has been. It was last semester because I took the time to write a different final. But it might not be that different this year.
But we're taking it separate from all the other sections.
Yep, because you're an evening class. Mm-hmm. Yep.
What are we allowed to bring for this?
Open note. I'm sorry, not open note. Open cheat sheet. One cheat sheet. One cheat sheet. One not open note. One cheat sheet. Okay. The other exam, the final exam is open note, open book. Right? Because that's the way they want it. Okay, so you'll have about 10 pages on. You'll not have 10 pages. 10 points on basically answering basically given this tree. Here's a bunch of relationships that I want you to define with nodes. So this is kind of the reverse of that question right over here. So answering the following vocabulary questions. What is the node at the top of the tree? It's the root. Right? That's worth a point, right? A point, no more than that, really. The links from a node to its successors are called what? Branches. Yeah, Might want to call them branches. It's a silly thing that you could look up for a point. The predecessor of a node in a tree is called what? Its parent. And if you have the same parent, you are siblings, right? It's the same. That's the nice thing about that relationship right over there. All right, so describe without using code, how do you calculate the height of a tree recursively? Right.
Depth from the left, the right, and then the max of, and then add the maxes together.
Get the depth of the
Plus
left.
one.
So yeah, get the depth of the left of tree and your right tree, right? So figure out which ones. So figure out what the size of your left tree is. Figure out what the size of your. So this is the get height function, right? Get the size of your left. Get the size of your right. Okay. Figure out which one is bigger and add 1 to that, right? This is a completely recursive function because each function is going to do that, right? And if you're an empty tree, you just return 0 as your height, right? So that might be something that might appear on the exam. Draw an example of each of the following type of binary trees. Use a different example for each possible tree, because technically this tree that I'm going to draw on the board is full, perfect, and complete, right? So all right. So let's give an example of each of a full tree, right? What does that mean to be a full tree?
Every node has 0 or 2.
You're answering a lot. So every node has what? Either 2 children or what? Yeah, 2 children, no children. So this is a full tree. This is a full tree. This is not a full tree, right? But this is a good example of a full tree, right? Every node has either 2 or 0. And then a complete tree is basically it's perfect on the top, and then right it's completely filled for the topmost levels, and then left to right it looks like this, right? Right, it's all the way filled in left to right, right? It's what you have to use for a heap, right? There's no gap here, so you can have a little empty spot, right? This is a complete tree. This is a complete tree. This is a complete tree, right? But if I were to do this, there's a gap here. This is not a complete tree. Remember, complete trees are how you build up heaps, right? And a perfect tree, well, it's something of height h, which has 2 to the h minus 1 nodes in it, which is just a mathematical way of describing it needs to look. Basically, that each level is completely filled, right? For each level of the tree, each level is completely filled, right? So this one's actually might be closer to 10 points or 7 points. I can't remember what I scored at. But this one is pretty much an exact same question as one you're going to find on the exam, only different numbers. The exact same question, but different numbers. Draw a binary search tree that forms after you insert the following integers, with 42 being first, right? So the idea here is that you add them from in this order, right? From left to right. You don't just choose whatever ones you want to insert. So let's go ahead and draw the tree that results from adding all of these numbers together. So we've got 42, and then we've got 10, so that goes to the left, and then 50 goes to the right, because that's bigger than 42, right? So 42, 10, 50, then 12. 12 is less than 42, greater than 10, so it goes over here. Then 17, less than, greater than, 17 goes here, right? 80, bigger. Okay. Negative 12 is less than everything that we put in, so it goes less than, so negative 12 goes right here. 100 is bigger than everything so far, so it goes all the way to the right. Okay. 96, so 96 bigger than this, smaller than this, so it goes over here, right? Bigger, it goes to the right, smaller, it goes to the left. until you hit an empty spot. It's really not something too hard. I'm always disappointed when I see like not minor mistakes are okay, right? You can make minor mistakes. Everybody makes a minor mistake when they're going through this quickly. But some people make utterly fundamental mistakes on this, and I just don't find an excuse for this because this is a very easy concept for this one. So 105, bigger, so bigger, 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 bigger. 105 goes over here, right? And then 86, so bigger than 80, smaller than 100, smaller than 86. Sorry, smaller than 96, so 86 goes over here. And I don't care if you're sloppy about it. We'll be able to recognize the correct answer, right? They're all going to have the same relative shape. 72, bigger than 42, bigger than 50, smaller than 80. 72 goes over here. All right. Did I make any mistakes, by the way? Because that would be really embarrassing at this moment. Okay. So that's your problem there. So your actual problem, your delete problem is different over here. So on the exam, it's going to be more like the quiz you took today. Given a tree, please draw what happens to the, so given a tree and deleting these nodes from this tree, draw the resulting tree. Here, I'm just saying work off the tree you had from the other answer. Okay. So first thing we need to do is remove 42. So when we remove an item from a tree, we've got to figure out how many children. We first got to find it. Congratulations, we found 42. And now we have to ask ourselves how many children it has. It has 2 children. And that dictates how we remove stuff. So with this one, we have to replace it with its next in order predecessor or its next in order successor. And I always like doing the next in order predecessor, which means we find the biggest thing that's smaller than it. So that means going 1 to the left and all the way to the right. Right? 1 to the left, all the way to the right, which is 17. And then we replace that with 17, and then we delete the 17 over here. We just remove it. Okay. Now we need to delete 12. Okay. So find 12. Go left. Go right. Right. 12 is less than 17. 12 is greater than 10. We found 12. Right. So now we need how many children does it have? It has 0 children. So deleting it is pretty easy. You just erase it. Okay. What about 17? The one we just moved up there. How do we delete that? Well, we have to find its next in order predecessor, which is the biggest thing that's smaller than it, right? So we go 1 to the left and all the way we can to the right, which is nowhere, right? So it's 10. We got to replace it with 10. Okay? So we got to replace it with 10, and 10 has 1 child, right? So first off, essentially, remember, the way it works is that we copy 10 over here, and we're kind of asking, so now how do I delete this? And the answer is, if you have 1 child, you let your parent adopt it. Right? It's not too bad. So remember, there's 3 rules. If you have 1 child, okay, if you have no children, just delete the node. If you have 1 child, let your parent adopt your child. Okay? If you have 2 children, find your next in order predecessor, which is the smallest thing that's bigger than you. Okay. Let it replace you, and then basically you handle now deleting that next in order predecessor at the bottom of the tree, which either has 0 children or 1 child. And if it has 1 child, you let the parent adopt it, right? You kind of recursively apply it. So, you'll probably get something like this, just the other way around. Like, so what is the following? Which of the following is a pre-order? Is the order for a pre-order traversal in a binary tree that has subtrees left and right? Right. Which one of these? Well, in order means that basically everything would appear in order, right? So which of these is the answer? B is pre-order. Yeah. Sorry, I was describing in order, unfortunately. No, I made a mistake. I read pre-order and then I said in order. So yeah, pre-order tree. Sorry, I messed it up. So I just made a mistake there. That's very easy for you to make, right? Make sure you're dealing with the right question. Pre-order means I deal with myself first and then my children. I could have sworn I read in order. So pre-order means I deal with myself first, then I deal with my children. Okay, what about post-order? What is the order for post-order? I deal with my children, then I deal with myself. So and the order is, and when I deal with my children, I always deal with the left tree first, then the right tree. Okay, so heaps. So for heaps, you can expect 2 7-point questions. Okay, they're going to be different than the question you get over here, which is simply describe how that works, right? On the actual exam, it's going to be something more along the lines of what you're going to have to do for trees, which is, given these numbers, build a heap from these numbers, right? Insert these numbers into an empty heap, right? And show me what happens. So be sure to practice that and understand how that works. So, and then the other one is, remove 2 items from the heap. So rookie mistakes I typically find, and which indicate you're in for a really bad time, people forget that heaps have to be binary trees, right? Or specifically complete binary trees, right? And that heaps work differently than binary search trees, right? So for a heap, the smallest thing is at the root. Yeah.
If for the test question you're having to throw out, would you rather throw it in the tree or leave the array?
I mean, either works, but I'm expecting the tree because that's easier to draw. But if you give me the array, I'll groan, figure out the right answer, and then I will. Or typically, I'll find somebody's test who is correct, who I've already marked correct, and then I'll read their answers left to right and compare them to yours because, we know because that's what we got to do. But however you want to think of it. But how does removing from a heap work? I put this first because it's the most common mistake I see on the exam. Yes.
Remove the root.
You always remove the root. That's correct. You never just remove any arbitrary item. You always remove the root. How does it get removed? You replace it with the not the biggest item, but you do replace it with it's not necessarily the biggest. You're kind of getting there, right? I understand what you mean, but it's not like explicit. Yes.
You replace it with the last item.
The last item in the complete tree, right? So, right, a complete tree is so remember, we're looking at a complete tree like this. Conveniently doing this is a heap. Conveniently, this is a heap, remember? And that's just simply a tree representation of the underlying array, which is 0, which it looks like this: 0, 1, 2, 3, 4, 5, 6, 7, right? So when we delete an item from the heap, what do? We remove the root, and then we replace it with this item, which isn't necessarily the biggest one. It was in this case. And then we need to reheapify this, right? We need to make sure if we turn this back into the heap property, that basically the smallest items at the root. So what do? We look at our 2 children and we swap with the smallest one, or if neither of them are smallest, we just smaller than we stay put. So we swap with the 1 goes up here and 7 bubble. It's a heavier item, so it bubbles down. Then 7 and 3 and 4. So we swap with 3. And so now notice that basically if we were to delete again, we'd remove 1, but 6 wouldn't necessarily be the smallest item, right? But what's important is that this complete tree structure is always maintained, right? I'll see students who hand me a tree like this, or a heap like this, and I just mark it completely wrong because the fundamental thing about a heap is its shape, right? Because it's just simply the visualization of an underlying array, and you read left to right in the array. So this would be the first index, second index, third index, and then you have a bunch of nulls, which doesn't work for a heap. So how does removal for a heap work? Describing the algorithm in detail. Remove the root, replacing it with the last item in the tree. And then while that item is bigger than either of its children, swap it with its smallest child. Repeat until you hit the bottom of the tree, or until there's no smaller child to hit, to swap with. How does adding work now? How does adding to a heap work? You just simply add it to the last spot in the complete tree, and then you bubble up if you need to, right? If it's a smaller item, it bubbles up, and you just simply swap with your parent until until you find something smaller than you, right? Here we just could add 1, and that's no problem. Sorry, we could add this item, and it doesn't need to go anywhere. For adding 0, on the other hand, 0, we would swap with 3, and 0 would swap with 1, because it was, while I'm bigger than my parents, I'm going to swap with my, while I'm smaller than my parent, I'm going to swap with my parent. The slides do a really excellent job on going into this. Huffman coding, right? So there's a reason why there's not a lot of coding on this. There's a lot of theory on this one, right? So consider a document that has the following symbols and frequencies. It has 50 A's, 40 P's, 20 L's, 70 E's, and 1X. So draw a Huffman tree for these symbols. So the first thing we need to do is arrange them in order, in a priority queue, right? By the frequency. So X is first because it appears the least, and then L, and then P, and then A. L, P, A, E. Okay? And then we need to just start combining them. So the way this building Huffman tree works, remember, is that there's a priority queue. So DQ the first 2 items, then combine them into a new tree. So X and L get DQ'd, and they combine, and their combined weight is, let's see, it was 120, 40, 50, and 70. So this new one has a combined weight of 21. So we reinsert this into the tree, and so we reinsert it over here, the combined one with the weight of 21, but because it's a priority queue, reinsert it into the queue, priority queue, not the tree. Because it's light, it skips to the front. So now we DQ this of these two, 21 and 40. So and that was a P, right? So the first thing you DQ goes on the left, the second thing goes on the right. This has a combined weight of 61. We put that into the tree, we put that into the queue, and it needs to reorder itself. It's not necessarily going to go to the front. So A and then dash. A and then the combined tree. And then this one, then we re-add that in. And then DQ E and the combined tree. Okay. Yes? It does. The first thing you DQ always goes on the left. The second thing goes on the right.
The smaller one goes
on the left. Yep, the smaller one goes on the left. Okay. And so now the second question is encode